The prism is a three-dimensional geometric shape made of glass. The sides of the prism are always polygons. That prism, which made of glass, come in many shapes, but the most common type is the triangle prism. In optometry, we use the triangle prism. They are useful clinical tools that refract light by changing the direction of incident light. The surface of the prism are flat, which means the prism doesn't affect divergence of light. And divergence, as you remember we said, it means, and divergence, if you remember we said, it means when the ray of light bends toward the optical axis or away from the optical axis. So the image will be clearer, sharper, bigger, or even smaller than the object. But that doesn't happen in the prism. The prism will only change the direction of the light without divergence. Since there is no divergence in the prism, that means there is no focal point. Those flat surfaces of the prism are angled in all ophthalmic prisms, and they meet at this angle. Let's call it A. For this prism and all ophthalmic prisms, light rays deviated toward the base of the prism. If we have the object here, when you take a look at that object through the prism, you will not see it in its real position. That means that you will see it through that prism is displaced toward the apex of the prism. So you will see it here, for example, and not in its real place. So the prism will form a virtual image that displays toward the apex of the prism. We have many types of prism. Reflection prism, or also we call them deviation prism, since they deviate the image toward the apex, such as in this example. We also have dispersion prism, and this kind of prism, the dispersion prism, separate the white light into its 7 colors. So if this our white light, since the red is the fastest, it will bend the least, and the violet is the slowest one, so it will bend the most. So you will see the rainbow when you will use this prism. We have other prisms such as rotation prism and displacement prism. Those three manipulate the location of the image, and they are common in imaging application, but the dispersion one only made for dispersing the light. Therefore, it's not suitable for any application requiring quality image. That's our prism. The prism composed of refracting surfaces. This is refracting surface number 1, and that's the second one. Both are flat. The angle between those two refracting surfaces is the refracting angle, and we can call it A. This angle also we call it apical angle. The tip of the prism, where the two refracting surfaces meet, we call it the apex. So the apical angle is at the apex of the prism. The base, which is the bottom of the prism, or the side opposite to the apex and the apical angle, we use it to determine the orientation of an ophthalmic prism.
So when we want to describe the direction of that prism, we relate it to the base of the prism. Here we have the incident ray. That incident ray should complete like that. But since it moved from one medium to another different medium, it will refract, which means change the direction. This is our normal, and normal, as we said, is the line perpendicular to the surface. Since that incident ray traveling from rarer medium, from air, to denser medium, which is glass, it will bend toward the normal. So this is the incident angle, which means this is the refracted angle. This is the normal again, which is perpendicular to the surface. This time, since the ray of light traveling from denser to rarer, it will refract away from the normal. So this is the second incident ray. So this is the second incident angle, which means this is the first incident angle. And so this is the second refracted angle, which means this is the first refracted angle. So in the prism, the light will refract at the first surface, then at the second surface. This is the first medium, which means with the first refractive index, and the prism has a different refractive index, then the light will refract to the third refractive index. Mostly, the first and third refractive index are similar, and mostly they are air, which means they will equal 1. The first refracted angle and the second incident angle both inside the prism, and that's why we call them internal angles. And the relationship between the two internal angles is related by the apical angle, which is A, equal the first refracted angle plus the second incident angle. So that apical angle equal the sum of the internal refracted angles. And since the behavior in the prism is refraction, that means Snell's law will take place here. And Snell's law states that the ratio of the sine of the incident ray to the sine of the refracted ray equals the ratio of the refractive index of the second medium to the refractive index to the. So we can do it like that. The sine of the incident ray multiplied by the refractive index of the first surface will equal the sine of the refracted ray multiplied by the refractive index of the second surface. Of course, here we are talking about angles. So we can use this formula in the prism here. I1 is related to R1 and I2 related to R2. Here we can use the Snell's law to say the sine of the first incident ray angle multiplied by the first refractive index will equal the sine of the first refractive ray multiplied by the second refractive index, which is here the refractive index of the prism. Let's also call it the refractive index of the prism to make it easier for you. And that's also means the sine of the second incident ray angle, this time multiplied by the refractive index of the prism, since it's inside the prism. So here the refractive index of the prism equal the sine of the second refractive ray multiplied by the refractive index here, which is the third refractive index. If refractive index number 1 similar to the refractive index number 3, for example, both are water, both are air, we can just say, instead of refractive index number 1 and refractive index number 3, we can just say refractive index of the surrounding space. But of course, when they are similar. With those formula, you can find different incident angles or refractive angles or even the apical angle. So let's have an example here. Let's say we have a prism made of plastic with the refractive index equal 1.49, and we place that prism inside water, so the surrounding space refractive index equal 1.33, and that's the refractive index of the prism, 1.49. So the ray emerged from that prism at angle of 25. And as I said, emerged from the prism, which means this is the second refracted ray angle. Let's find the incident angle at the first refracted surface of the prism. So we can draw it to make it easier. That prism with refractive index 1.49 and it placed in refractive index of water equal 1.33. The light here emerged with angle 25 degrees and we need the incident ray here. By using the Snell's law and knowing the apical angle, we can find that missing incident ray. So the first step, since we know the second incident ray, first step is to use this one, the sine of the second incident ray multiplied by the refractive index of the prism, which 1.49 equal sine of 25 multiplied by the refractive index of the surrounding space, which is water, and it's equal 1.33. So with calculation, here the result is 0.5621 above 1.49. After calculation, this one equal 0.3772. And the angle that has this sign is 22.16 degrees. So the second incident ray equals the reverse of this sign of 0.3772. This equals 22.16 degrees. So this second incident angle here is 22.16. In the second step, we said the apical angle equals the two internal angles, R1 plus I2. And here we have the apical angle. Oh, I'm sorry, I didn't give you that one. It's unknown. So let's say the apical angle equals 40 degrees. So we can use it here. The first refracted ray equal the 40 degree minus 22.16 degree. The first refracted ray angle equal 17.84. Since we have this one now, we can depend or rely on this one. And that's the third step. We say the sine of the first incident ray multiplied by the refractive index, which is here the water, 1.33, equal the sine of 17.84 multiplied by the refractive index of the prism, 1.49. And the result is 0.3432. The angle that has this sign So reverse sign of this one, 20.07 degree. So the light strikes that prism at angle 20.07. The angle here is 20.07 degree. So far as you can see, the prism depends on the incident ray, on the refractive index of the prism, and the surrounding space, and most importantly, the apical angle. If apical angle less than 10 degree, immediately considered as thin prism. So thin prism is the prism that had apical angle less than 10 degree. Each material has a specific critical angle, and the critical angle means the least angle of incidence at which total reflection takes place. And that critical angle will become smaller with the higher refractive index of that medium. For the prism or the glass that we use to produce the prism, the critical angle is 42 degree, where the precise number is 41.8. But let's count it as 42. That's the critical angle for the prism glass. For medium with higher refractive index, such as diamond, which has refractive index equal 2.4, the critical angle for the diamond equal 24.6 degree. So when the refractive index increase for the medium, its critical angle will become smaller. So here the prism and the critical angle is 24 degree. If that's our incident ray. If it enters that prism at angle more than 42, let's say for example at angle 50 degree, the light then, when it wants to travel from higher index from the prism to lower index or rare index, which is air, since the incidence angle is more than the critical angle of the prism, which is more than 42, the light here will trap and it will not refract, but will reflect like that to cause total internal reflection. So the total internal reflection occurs inside the medium when the angle of the incident ray more than the critical angle of that medium. So the light will trap inside that prism and it will not refract. Here in diamond, the incident ray should strike the diamond at angle less than 24.6. Otherwise, the light will trap here, and that's why always the diamond is shiny because of the internal reflection or total internal reflection. If we saw our example, this is our incident ray, strike the prism at angle less than 42, which means there will be no internal reflection. The light will refract and leave the prism easily.
What if we have a prism, one of its surfaces perpendicular to the base, such as this one for example? The first surface perpendicular to the base of that prism, or the second surface is perpendicular to the base. When we have a flat surface and the light strikes that surface at right angle, it will not refract. So the incident angle there equals 0. And the emergent ray also equals 0 since there is no refraction. The same occurs here in the prism. If the first surface is flat, the light ray that strikes that surface will not refract. So the incident angle here will equal 0, which means the refracted angle also will equal 0. But since the light also will refract at the second surface, and the second surface angled here, not at right angle, that means we will have a second incident angle and we have a second emergent angle. Those two does not equal 0 since the refraction took place here, which means the angle, the apical angle, will only depends, which means the apical angle A will only depends on the second incident angle. So A in this situation will equal the second incident angle only. And this ray at right angle to the first surface, we will call it normal incident ray. In the second case, the incident ray will strike the prism not at right angle. Here is our normal. Here is our normal. So our incident angle does not equal 90 degrees. But since the second surface is flat, that emergent ray will exit the surface at right angle also, which means it will not refract. The light here will not bend. So in this case, the second incident angle and the second refracted angle both equal 0, since the light will not refract. And here we will call this ray normal emergent ray. So normal emergent ray is the ray that leaves the prism without refraction. With normal emergent ray case, this one, the first incident angle will not equal 0, neither the first refractive angle. So in this case, A will depend on the refracted angle here. So A here equal the first refracted angle only. When we have a prism, and this is our incident ray, that ray should finish like that, but because of different medium, from rarer to denser, the light will refract toward the normal. And since the light now moving from denser to rarer, it will refract away from the normal. This ray should have finished like that. So this is our first incident angle, and this is our first refracted. This is our second incident angle, and this is our second refracted angle. The angular bending that the incident ray undergoes after refraction through the prism is called the deviation. That incident ray should have gone like that, but because of refraction, it bent like this. So this amount of bending, we will call it the deviation. And let's call it deviation angle number 1. Of course, the same will go here. The light should have gone like that, but because refraction took place, the light deviated from its first trace away from the normal, and the amount of deviation this time, let's call it deviation angle number 2. The larger the deviation, the more the incident ray is bent and the higher the prismatic power. This deviation is used to describe the power of the prism. And the power of the prism just means when the prism changes the location of the image. That's all. In prism, we don't have Bergen's power. And the prism also doesn't have focal point since it doesn't have Bergen's power. So no focal length also in the prism. Those two are not found in the prism. The power of the prism, we also measure it by diameter. And to differentiate between prism and normal lenses, thick, thin or even cylinder lenses, we put this sign, the triangular sign, before the number. So triangle 5 diameter, that immediately means we have prism with power 5. But what do we mean by prism with power 5 diameter? If I want to count the whole deviation, start from the deviation of the incident ray, this one, plus the deviation of the refracted ray, the sum of those two will give us the total deviation amount. So the deviation angle, the total one, will equal deviation angle number 1 and deviation angle number 2. And since it depends on the incident emergent rays, that deviation angle, the total deviation, will equal also the first incident ray plus the second refracted ray. And of course, it will depend also on the internal angles. Since A, the apical angle, equals the sum of the internal angles, that means we can rely on A instead of using the internal angles. But we need to subtract that apical angle to have the total deviation. At some point when we have different incident rays at different angles, one of those incident angles will equal the angle of emergence here. Let's draw another prism. This is our normal here and here. When an incident ray strikes the prism at angle equal to the angle of emergence later, which means the first incident angle equal the second refracted angle, this will cause the minimum amount of deviation. And with that case, the light ray inside the prism will be parallel to the base of the prism. So when this first incident angle equals the second refracted angle, the ray inside the prism parallel to the base of the prism, and this case we call it the minimum angle of deviation. For thin prism in air, the relationship between the minimum angle of deviation, the apical angle, and the refractive index of the prism will equal the apical angle multiplied by refractive index of the prism minus 1. This one equals the minimum angle of deviation. So, since it depends on the refractive index of the prism when we place it in the air, will that minimum angle of deviation change if we place it inside water, for example? Yes, it will change. And the result here will be in degrees, not in diameter. And why we need to find the minimum deviation angle? Essential and important because we obtain a bright and distinct spectrum and magnification in unity. So the distance of the object and image from the prism is same. So briefly, it's important to give a bright, clear image. But again, what that 5 diameter of prism means. So this is the prism, and that's our incident ray and emergent ray. The light should have finished like that, but it refracts and change the direction with amount of deviation. Let's say we have plane here. After 1 meter, the prism deviates the light ray 1 centimeter away from the original path of light. So the prism that deviates a light ray 1 centimeter at a distance of 1 meter is said to have a power of 1 prism diameter. Or we can write it like that. 1 prism diameter. So when I have prism 5 diameter, this means the amount of deviation at 1 meter distance will be 5 centimeter, not just 1 centimeter. So if we have image here or object here, and you take a look through a prism, you will not see the object in its real position. If the power of this prism 1 diameter, you will see the image 1 centimeter deviated from its real position. If the power of this prism 5 diameter, the displacement of this image will be 5 centimeter. So you will see down there. The power of the prism just displaces the images, doesn't make it clearer. If you have refractive error and you need glass, and this image is not clear, you need to put the glass here, spherical, cylindrical lens, any lens with divergence power to make the image clearer. But the prism will just change the location of that image, doesn't make it clear. How can we determine the power of the prism in prism diameters? So if we call this 1 meter or this distance y, and the displacement from the normal, let's call it x. The power of the prism depends on the distance at which the deviation is measured, which is y, and the distance that the light ray is deviated, which is x. So the power of the prism, let's use the symbol, equal 100 multiplied by x over y. And as we said, x is the deviation amount and y is the distance that we measured the deviation at. This one will give us the dioptric power of the prism. In triangles, this x over this y equal tan of this angle. So the prismatic power in diameters also equal 100 multiplied by tan of the deviation angle. This one can be used too. So for example, I have a prism that deviates the light ray 6 centimeter at distance 500 centimeter, which means 5 meter. What is the power of the prism? P equal 100 in this formula. Although the power of the prism in diameter, but here we don't have to convert those measurements into meters, but we will use them in centimeters, because the scientist who measured the power of the prism in diameters, he measured 100 centimeters from the prism. So in prismatic power, not in the lens power, the measurement of distance we use the centimeter, not meter. In lens power, we measure the distance by meter. So lens power, the distance by meter. The prism power, we measure by centimeter. Mostly anything by meter, but here in prism we measure it by centimeter. We already have it here in centimeter, so 100 multiplied by 6 centimeter divided by 500 centimeter. So the power of that prism equal 1.2 prism. We can just leave it like that, or we can write the diameter, but mostly we just leave it like this. We can immediately understand it, 1.2 prismatic power. But don't forget this sign of prism, the triangle.
In ophthalmic prism, we need not just to determine the power of the prism, but also the orientation of that prism. We rely on the base of the prism and the nose of the patient. So that's the face of the patient, and this is the inner angle of the eyes, which is on the nose side. This is the inner side, and this is the outer side. So when I put the base of the prism like that, the base of the prism now at the inner angle of the eye. So we call it base in. For the right eye, if I put the base at the outer angle of the eye, now the base is out. If I place that base of the prism upward, the direction of this prism is base up, and if I place it downward, we call it base down. So we relate the orientation of the prism on the base, and the image will displace toward the apex side, which means if this is my eye with the nose here, and I place the prism in, the eye will move to become in this area toward the apex side. The opposite, if I place the prism out, this time the eye will move toward the nose. If you notice, when we have the spherical lenses, the convex one and the concave one, they are little bit look like the prism. The concave one look like two prisms base out, and the convex one look like two prisms base in. Take a look at this video. When we put a lens and we move it in all directions, you can see the prismatic effect of that lens. This time, let's try the concave lens. Prismatic effect. And we use this property to do the neutralization. That prismatic effect of the lens could be really annoying. So to prevent it, we need to place the middle of the lens with the center of the eye. Because towards the center of the lens, that prismatic effect decreases and there is no effect on the middle of that lens. Neither in concave lens nor the convex lens. So when looking along the optical axis of the lens, there is no prism power. But when viewing through more peripheral regions of the lens, there is prismatic power effect. And that effect will increase as the distance from the optical center increases. To calculate the amount of this prismatic effect, we use a formula, we call it Prentice rule. The prismatic power of the lens at any point on the lens equal to the distance of that point from the optical axis in centimeter multiplied by the power of the lens in diameters. So again, as we said, the distance in prism, we measure it by centimeter. And this relationship is known as Prentice's rule. For example, a patient wearing a glass with plano power at sphere plus 4 cylinder axis 180. If that patient has been decentered 3.5 millimeter temporal and 2.5 millimeter superior to the pupil. First of all, what do we mean by temporal? If that's the nose of the patient and those are his eyes, this is the nasal side and the outer angle we call it temporal side. This is the center of the eyes, which is the pupil. Upward is the superior. Downward, inferior. Since in cylinder we have the power perpendicular to the axis, that means on the horizontal meridian we don't have prism power. But for vertical meridian, the decentration superior is 2.5 millimeter. So that prismatic power of the lens equal the distance from optical center by centimeters. So here we need to convert it to centimeters. That's equal 0.25 centimeter multiplied by the power of the lens, which is plus 4. So the prismatic effect at that point equal 1 prism. If that lens was sphere, let's say plus 4 sphere, this means at the horizontal meridian we also will have a prismatic effect. So as you can see here, we use prism to correct strabismus. Strabismus means misalignment of the eyes. To see a beautiful three-dimensional image, those eyes of you need to move together. But sometimes misalignment occurs, which means you will find one eye here in the normal position, but the other one is here. Or it could be here. So that's misalignment. How can we fix that? By using suitable amount of prism in correct orientation, base in, base out, base down, or base up according to the situation. So in optical prism, we need the power of that prism, 4 prism for example, plus the orientation of that prism. What if I need to put 2 prisms? For example, this patient is alignment, not just horizontally, but also vertically at the same time. So the eyes like that, horizontal but also vertical. The strabismus here, up and to this horizontal direction. So we need 2 prisms to fix that. So we will do combination, which means we will use 2 prisms at the same time. So this is the prism, and that is our normal, and that's our amount of deviation. For measurement, let's say this is y, and this is the amount of deviation, which is x. So the power of that prism will equal 100 amount of deviation above the measurement divided by the distance that we measured the deviation at. Or we can say, since this angle of deviation, we can say the power of the prism equal 100% multiplied by tan d. So if I put or combine 2 prisms at the same direction, let's say we have 2 prisms base down. This is our light deviated by this amount. This light should have finished like this, but it refracted by the 2 prisms. To find the whole deviation amount, we will count the deviation of the first prism. We will count the deviation of the first prism, which is here, this one, and the deviation by the second prism. So this will give us the total deviation. If they are 2 at the same direction, for example, this is 3 prism and this is 4 prism, and both are base down, we can easily add 3 to 4 prism, and this will give us the total deviation. So the total deviation here is 7 prism, which means when they are both at the same direction, we can easily add the first prismatic power to the second prismatic power, and this will give us the total power of those combined prisms. And most importantly, we need to remember the direction of the prism. So here we said they are base down, so the power here 7 prism base down. Okay, what if they are the base directions of the 2 prisms are opposite? For example, one base down, and let's say it's 3 prism, and the other one is 4 prism, but this time it's base up, which means the light will deviate like that, then go back again like this. Since the light deviated by the prism will deviate toward the base. In this case, we'll subtract the prism diameters. So the resultant here, the total power will be just 1 prism only. And since the up more than the down, this one will be one base up. So if the directions of the two prisms are different, we will subtract. And here we will not care about negative or positive. 3 minus 4 is minus 1, but we don't care about that here in our prism. The last case, when we have two prisms, but one oriented vertically and the other one horizontally. So for example, let's say we have 3 prisms base in combined with 4 prisms base up. Base in, as we said horizontally, we determine by the nose. So this is the nose. Since it's base in, that's the direction of the prism. Here is our base. Here we will depend on Pythagoras' law. First thing here, we need to find the orientation of those two prisms by using this one. So this prism oriented horizontally, let's write it here, and the other one oriented vertically. In triangles, when you have angle you want to find it, let's say this is D, the tan of D equal the vertical one, let's write it here, divided by the horizontal one. So the same here, tan of the angle that we wanted equal the vertical one here is 4 divided by the horizontal, which is 3. And the angle that has the result of this one is 53.1 degree. And then we can use Pythagoras' law when we want to find this. Let's call it the total power of prism. The total prismatic power here equal the second root of the horizontal square. So the power of the horizontal prism square plus the power of the vertical prism square. So 3 square plus 4 square under the root, the result will be 5. So the resultant prism out of two different orientation, one vertical and the other is horizontal, will equal 5 prismatic power. And since this one is bigger, that means 5 prismatic power base up at angle 53.1 degree. So as you can see here, we use prism to correct strabismus. And strabismus means misalignment of the eyes. To see a beautiful three-dimensional image, those eyes of you need to move together. But sometimes misalignment occurs, which means you will find one eye here in the normal position, but the other one is here. Or it could be here. So that's misalignment. How can we fix that? By using suitable amount of prism in correct orientation, base in, base out, base down or base up according to the situation. So in optical prism, we need the power of that prism, for prism for example, plus the orientation of that prism. What if I need to put two prisms? For example, this patient is alignment, not just horizontally, but also vertically at the same time. So the eyes like that, horizontal but also vertical. The strabismus here up and to this horizontal direction. So we need two prisms to fix that. So we will do combination, which means we will use two prisms at the same time. So this is the prism, and that is our normal, and that's our amount of deviation. For measurement, let's say this is y, and this is the amount of deviation, which is x. So the power of that prism will equal 100 amount of deviation above the measurement divided by the distance that we measured the deviation at. Or we can say, since this angle of deviation, we can say the power of the prism equal 100% multiplied by tan d. So if I put or combine two prisms at the same direction, let's say we have two prisms base down. This is our light deviated by this amount. This light should have finished like this, but it refracted by the two prisms. To find the whole deviation amount, we will count the deviation of the first prism. We will count the deviation of the first prism, which is here, this one, and the deviation by the second prism. So this will give us the total deviation. If they are two at the same direction, for example, this is 3 prism and this is 4 prism, and both are base down, we can easily add 3 to 4 prism, and this will give us the total deviation. So the total deviation here is 7 prism, which means when they are both at the same direction, we can easily add the first prismatic power to the second prismatic power, and this will give us the total power of those combined prisms. And most importantly, we need to remember the direction of the prism. So here we said they are base down, so the power here 7 prism base down. Okay, what if they are the base directions of the two prisms are opposite? For example, one base down, and let's say it's 3 prism, and the other one is 4 prism, but this time it's base up, which means the light will deviate like that, then go back again like this. Since the light deviated by the prism will deviate toward the base. In this case, we'll subtract the prism diameters. So the resultant here, the total power will be just 1 prism only. And since the up more than the down, this one will be 1 base up. So if the directions of the two prisms are different, we will subtract. And here we will not care about negative or positive. 3 minus 4 is minus 1, but we don't care about that here in our prism. The last case, when we have two prisms, but one oriented vertically and the other one horizontally. So for example, let's say we have 3 prisms base in combined with 4 prisms base up. Base in, as we said horizontally, we determine by the nose. So this is the nose. Since it's base in, that's the direction of the prism. Here is our base. Here we will depend on Pythagoras' law. First thing here, we need to find the orientation of those two prisms by using this one. So this prism oriented horizontally, let's write it here, and the other one oriented vertically. In triangles, when you have angle you want to find it, let's say this is D, the tan of D equal the vertical one, let's write it here, divided by the horizontal one. So the same here, tan of the angle that we wanted equal the vertical one here is 4 divided by the horizontal, which is 3. And the angle that has the result of this one is 53.1 degree. And then we can use Pythagoras law when we want to find this. Let's call it the total power of prism. The total prismatic power here equal the second root of the horizontal square. So the power of the horizontal prism square plus the power of the vertical prism square. So 3 square plus 4 square under the root, the result will be 5. So the resultant prism out of two different orientation, one vertical and the other is horizontal, will equal 5 prismatic power, and since this one is bigger, that means 5 prismatic power base up at angle 53.1 degree.